Welcome back, folks. This is the third segment of for section 5.2. We were in the middle of doing a series of proofs using basic fundamental identities. I'm just going to dive right into it. I've looked over the material that I have to cover, and I think it might benefit people if I actually add a few more, possibly a few more segments with more practice on identities. So I think this probably is not the last segment, although I may cover most of my prepared materials. We'll just see where we land at the end of this video, but I'm probably going to come back with at least one or maybe even two more. Anyways, so this is still section 5.2, and I believe we are now on page 7. So let's just dive right in. This is example number 4. Let's show that the following expression, or this following equation holds, that it is an identity. Let's take secant of x plus tangent of x all over sine of x, and show that that is equal to cosecant of x over secant of x minus tangent of x. Okay, so just pause a second. Recall with the first couple of steps in this is we want to try to determine, at least to some extent, which side is more complicated, and they both look pretty complicated, right? They each have 3 unique trig functions. They both involve addition and subtraction, and they both have fractions in them, or rational expressions. So it's hard to really say which side is more complicated. But what I'm going to point out to you is that it really doesn't make any difference. We just need to pick one and start going. However, I would say that having a binomial in a denominator of a fraction is a little more complicated than having a binomial in a numerator. And so that discussion alone is the only reason why I'm going to start with the right-hand side. Okay? So we'll start with cosecant of x over secant of x minus tangent of x. Okay, there's our right-hand side. Now, you may recall that that I mentioned it's perfectly legitimate to multiply by 1. Now, it just so happens, I want you to think back when it comes to rationalizing denominators from algebra, where you have like maybe a square root in the denominator or something, that you would multiply by something called the conjugate to get rid of that radical. Well, I want you to think back about most of these trig functions, because they're based fundamentally out of the Pythagorean theorem. They have a lot of square roots as exact values, and so this kind of leads us to this idea that maybe if we treat this like some sort of a conjugate process, or some sort of a radical in the denominator, and use the same sort of techniques we used in algebra to rationalize denominators, that maybe that's a solution. And so I alluded to it previously, but now I'm going to use that technique formally. Okay, so what I'm going to do here is I'm going to write cosecant of x over secant of x minus tangent of x, and I'm going to multiply this by the ratio of the first, in the denominator, it's the first term minus the second term. I'm going to multiply by the conjugate, what I call the trigonometric conjugate, which is the first term plus the second term. So I'm going to multiply by the ratio secant of x plus tangent of x over secant of x plus tangent of x. Now notice this is just a really ugly version of the number 1, right? Which is, as we said in our sort of preamble in the first segment to this, that's always legitimate. So, all right, so then what's the next step here? Well, what I'm going to do is I'm going to leave the numerator undistributed for the time being. So I've got cosecant of x times the quantity secant of x plus tangent of x. Now notice I haven't done any trig yet. This is just simply algebra. Now when I multiply a minus b times a plus b, remember this is the factorization for a difference of squares. So my denominator, when distributed out, is going to be secant squared of x minus tangent squared of x. Okay, and I want you to take just a minute and think back to the second Pythagorean identity. What is this quantity down here? As you recall, the second Pythagorean identity says tangent squared plus 1 is equal to secant squared. So what then is secant squared minus tangent squared? Just think about that a second. It's actually equal to the number 1, right? So the denominator essentially disappears. And so I'll just rewrite the numerator all over 1, right? That's kind of a neat trick. And this is, anytime you see these paired binomials, that is sort of let's see if that works, kind of try it and see what happens sort of thing. But this is a Pythagorean identity, right? So the next step then is to perform a little bit of algebra. I'm going to distribute these two terms. Now that I just have the numerator, I mean the denominator goes away. So I'm going to distribute the numerator terms and see where that gets me. So I have, it's now cosecant of x times secant of x plus cosecant of x times tangent of x. Now, this is where, and that's just algebra, right? So now I want you to think a second about where we were headed, right? Notice, well, I guess maybe this step, see, this happens a lot. This step is not actually necessary. I apologize for that. Because we're already, with this form where it's factored, looks an awful lot like where we were headed. Notice that the difference is just that we have a sign in the denominator and we have this factor in the numerator. This should be a pretty easy substitution. Basically, we're going to transform cosecant into the reciprocal of sine, and we should be pretty much done. So I'm going to do that in 2 steps. I mean, you could probably do it in 1, but I'm going to write it this way. So the reduction, the 1 in the denominator just basically goes away. It's not necessary to write that. And we're left with this substitution. 1 over sine of x times secant of x plus tangent of x. And this is a reciprocal identity, right? This is starting to look an awful lot like the left-hand side. So really, I'm just going to write it in a different form where we have secant of x plus tangent of x all over sine of x. And this is an algebraic step. Now, would it absolutely be critical to do both of these steps? Probably not, because it's pretty clear what's happening here as long as you had the proper justification. But notice there are 2 different processes going on here. It's both a reciprocal identity and an algebraic step. But this is the goal. We started with in this case, the right-hand side, and through a series of justified arguments, we end up with the left-hand side. So this proof is done. Okay, of course, that page will be available for y'all on Blackboard here once I get this completed. So next, I just wanted that was the 4th of the sort of direct proofs that I had set up for us. Now, I want to make just sort of an observation. We've already had a couple of situations where I've said, you know what, both of these sides, they look kind of complicated, and it may not make sense to it may be kind of challenging to get them get from one side to the other. It's and you remember the term that I used is complexify, right? It's hard to complexify. Once you get something boiled down to something that looks sort of simple, it becomes challenging to then make it complicated, right? Which is why you end up with, when both sides look sort of complicated, you can get stuck. So here's sort of a logic argument. So I just kind of an aside. If you're wanting to show that statement A must equal statement B, what we've done so far is to start with one and go dink, 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 dink through a series of logical arguments and end up with B. That is logically fine. Alternatively, we could prove two things. We could prove that A is equal to a third statement and B is equal to a third statement. This is actually two different proofs. Okay, so we would, instead of A going straight from A to B or from B to A, sometimes it is easier just to take A, simplify it as much as possible till you get to expression C, and then start over again with B and show that it equals the same simplified expression. Okay, that's a pretty standard technique. So that's what I'm going to use here in the next, the next, well, let's see how many examples I have. Probably, well, this one's kind of a little long. So I'll just probably have this one, and then we'll see where we're at. So let me start by stating it. Show that cotangent of alpha minus cosecant of alpha over cotangent of alpha plus cosecant of alpha is equal to the expression 1 minus 2 times cosine of alpha plus cosine squared of alpha all over minus sine squared of alpha. Okay? Now note, both of those sides look kind of complicated. I would argue that if you were taking this from a purely objective standpoint, probably the left-hand side looks more complicated. And so there would be a tendency to want to start there, recognizing that the right-hand side has nothing but sines and cosines in it. We did this sort of thing before where it's like, well, you know, since this doesn't have sines and cosines and that does, I already know kind of a first step that maybe if I convert this all to sines and cosines, I might end up with something that gets me a little closer to the right-hand side. So that's a good place to start. But what you're going to find is that you get to a point where you don't really know what to do anymore. Okay, so let's start with the right-hand side. Cotangent of alpha minus cosecant of alpha all over cotangent of alpha plus cosecant of alpha. Okay, now the first thing I'm going to do is I'm going to use quotient and reciprocal identities to turn this all into sines and cosines. So this ends up being cosine of alpha over sine of alpha. That's the cotangent. Minus 1 over sine of alpha all over cosine of alpha over sine of alpha plus 1 over sine of alpha. Okay, this is what, a quotient, reciprocal and quotient. So this is something that when we talked about this originally, this is this sort of standard practice. Take a bunch of weird trig functions, turn them into ratios and sums and differences of sines and cosines. Okay, so now note, look at the expression we have. This is a complex fraction, but all the internal fractions all have the same denominator. Right now, we've talked about this technique where if you want to simplify a complex fraction, you multiply by every term by the least common denominator of all of the interior terms. Now, since they all have the same denominator, this is going to make this really easy. They basically go away. So the very next step is to reduce this down to cosine of alpha minus 1 over cosine of alpha plus 1. Okay, and that's just an algebraic step. So the question then becomes, how in the world am I going to get this out of that? Well, there is a way to do it, but it's not something that's necessarily going to be real intuitive. Okay, so maybe another approach then is to start with this side. Now, see basically what we've done is we take something that looks complicated and made it simpler. Notice there's two different trig functions here, both of which are the less comfortable ones. Here there's only one, and it happens to be cosine, which is more comfortable, generally speaking. Okay, so what I'm going to propose is, rather than trying to complexify this term, how about I just pause and then start over with the right-hand side and see if I can't get the right-hand side to look like this. So I've kind of run out of space here on the page. I'm gonna move to a new page and pick it up from there. So just to repeat what I had, and I'm going to kind of repeat this here. What I'm wanting to do now, sort of as my second step here, is I'm wanting to show that this expression is equal to this expression. And so I'll rewrite that on page 9, just so it's clear what's going out. So I would say maybe step 2, show that, and the expression, the right hand side expression was 1 minus 2 cosine of alpha plus cosine squared of alpha over minus sine squared of alpha. We wanted to show that this is equal to the intermediary, the thing that we just boiled the left-hand side down to, which happens to be cosine of alpha minus 1 over cosine of alpha plus 1. Okay, so this is now our new task. And obviously here, it's clear which side is more complicated. The left-hand side, no question, is more complicated. So let's just start down that road. Starting with 1 minus 2 cosine of alpha plus cosine squared of alpha over minus sine squared of alpha. Now, remember I had said previously, be looking for ways to factor. This right here happens to be a different, this happens to be a perfect square, right? This will become 1 minus cosine quantity squared. That's one way to think about it. Alternatively, we have this negative sign that's in the denominator that's really kind of driving me a little bit crazy. But we'll get to that eventually. So what I'm going to do is I'm going to factor this numerator and just see what comes out of this. So again, this is sort of a squared minus 2ab plus b squared. And so this will factor as 1 for a minus b quantity squared. Okay, and then the denominator, nothing changes. That is a purely algebraic step. It's just factoring. The next thing that I'm going to do, and there's a reason why I'm doing this. Notice that, see that numerator in both of these expressions is very, very similar. And that might take care of that negative sign too. Okay, so now one thing to consider is that the target expression only has cosine in it, but the expression we currently have has sine. So maybe there's a way to get that out. And what my suggestion, as I've said before, whenever you have a trig function squared, be looking for a way to apply a Pythagorean identity, okay? And it just so happens that minus sine squared is going to be cosine squared minus 1, okay? And you can work that out for yourself, but that's the reality. So this expression now becomes 1 minus cosine of alpha quantity squared divided by cosine squared of alpha minus 1. And that is a Pythagorean identity. Okay, so now what? Well, notice down here that this is now a difference of squares, right? This is a squared minus b squared, or b squared minus a squared, whichever way you want to think of which one's a and b. Let's factor that. So we end up with 1 minus cosine of alpha quantity squared up top, and in the denominator we have cosine of alpha plus 1 times cosine of alpha minus 1. And this is just algebraic factoring, right? So this is starting to look an awful lot like the target, right? We've already got the denominator of the target sitting there. So hopefully there's some kind of cancellation that occurs here. And if you recall from algebra, these binomial, I mean, they're the same binomial except for there's a negative sign in them, right? So when you cancel one factor of 1 minus cosine alpha by reducing it by this term cosine alpha minus 1, instead of becoming 1, it actually becomes minus 1. So I'm going to write that. It's probably been a while since you've done one of those. So I'm going to go ahead and maybe let me use a slightly different color to show what I'm doing. Okay, so I'm canceling one factor of the numerator and the factor in the denominator, and those are becoming minus 1, right? Because they have an opposite sign. Okay, so to express that, then the next term is going to be negative 1 times, well, I still have one factor of 1 minus cosine of alpha, and in the denominator I have cosine of alpha plus 1. Now look again at what the target is. The target is cosine alpha minus 1 over cosine alpha plus 1. If I simply distribute this negative sign, I'm going to have the target. By the way, this was purely an algebraic step. So the target then, by distributing the negative 1, changes the signs of everything in the numerator. We have cosine of alpha minus 1 over cosine of alpha plus 1. Okay, and this is just, again, an algebraic step. And I did them very concisely because I wanted you to see every single piece of this. This is starting to get into a little bit more complicated algebra. So to summarize, let's see what we did here. Back on page 8, we started with the left-hand side, and we boiled that down to a third expression. Okay, then we started with the right-hand side and boiled that down to the exact same expression. Logically, that is equivalent to starting with the left-hand side and ending with the right-hand side. Okay, and so this proof is done. Okay, that was kind of a little bit of a challenge. I'm going to stop the video here. I'm going to come back at least one more segment and just do as many proofs as I can until I just get tired of it. We will see you next time.